To test this, Volta systematically experimented with pairs of metals and conductive fluids. He showed that certain metal combinations, for example, zinc and silver, produce stronger effects than others when connected by brine-soaked cloth or cardboard. He also developed devices like the electrophorus to generate and accumulate charge. The crucial step came in 1800. Volta realized he could repeat the basic metal electrolyte metal unit in a stack, aligning many such cells in series. He built a column of alternating zinc and silver, or copper, discs separated by discs of saltwater-soaked cloth. When the top and bottom of this voltaic pile were connected with a wire, a steady current of electricity flowed. Sparks could be drawn repeatedly, wires warmed. Chemical changes occurred in liquids touched by the circuit. This was radically different from anything before. The pile did not merely store static charge. It generated a continuous, sustained current as long as the chemical differences between the metals and the electrolyte lasted. Volta wrote to the Royal Society in London, describing his invention. News spread rapidly through Europe's scientific networks. The Society awarded him the Copley Medal. Napoleon Bonaparte invited him to Paris, honored him publicly, and helped cement his fame. The unit of electric potential, the volt, later took his name. The impact of the voltaic pile was immediate and profound. In laboratories from London to Paris, investigators now had, for the first time, a portable, controllable source of continuous electricity. Even as Galvani and Volta argued over sources of electricity, another Frenchman was making it quantitative. In 1785, Charles-Augustin de Coulomb published work based on a delicate torsion balance, a horizontal bar suspended by a thin fiber. By placing small charged spheres at its ends and bringing another charged object nearby, he could measure how much the fiber twisted. From these careful measurements, he derived a mathematical relationship. The force between 2-point charges is proportional to the product of their charges and inversely proportional to the square of the distance between them. In modern notation, F is proportional to R2Q1Q2. This inverse square law for electrical force echoed Isaac Newton's law of gravitation. It suggested that electric phenomena, like celestial mechanics, could be described in precise mathematical terms. Coulomb also clarified the behavior of conductors and insulators, and the idea of charge distribution on surfaces. Earlier, the English experimenter Henry Cavendish had done similar work, but left it largely unpublished. Coulomb's work became the foundation that others used. By the end of the 18th century, thanks to Coulomb, electricity was not just sparks and shocks, it was a measurable interaction obeying quantitative laws. Volta's pile did more than prove a theory, it opened a toolbox. In London, at the Royal Institution, chemist Humphry Davy quickly built vast assemblies of voltaic piles, batteries in the modern sense, made of hundreds or thousands of individual cells. With these powerful sources, he and his assistants pushed electricity into chemistry. Others had already seen that passing current through water caused bubbles to form. In 1800, William Nicholson and Anthony Carlisle used a voltaic pile to electrolyze water, splitting it into hydrogen and oxygen. Davy went further. By passing strong currents through molten salts like potash and soda, he succeeded in isolating new elements. Potassium from potash and sodium from soda in 1807. Magnesium, calcium, strontium, and barium in 1808. These were the first elements deliberately isolated by electrical means. Electricity had become a chemical tool, revealing previously unknown building blocks of matter. The line from Volta's modest stack of disks to entire fields of electrochemistry and battery technology runs straight through these early 19th century experiments. As the 18th century closed, electricity had been transformed in several key ways. From static sparks to stored charge, Leyden jar. From isolated shocks to measured forces, Coulomb's law. From episodic discharges to continuous current, Volta's pile. From parlor entertainment to practical protection, lightning rods. From mysterious influence to a tool that could break apart chemical compounds, early electrolysis. A scientist around 1800 could store charge in a Leyden jar, quantify attractive and repulsive forces between charges using Coulomb's torsion balance, generate a steady current with Volta's pile, use that current to decompose substances and discover new elements. The phenomenon that had once been known as a strange electric fluid was now part of a coherent system: charges, forces, conductors, insulators, currents, and devices. The 18th century did not yet have motors, telegraphs, or power grids. That would require new connections. In 1820, the Danish physicist Hans Christian Ørsted noticed something unexpected during a lecture. A wire carrying current seemed to deflect a nearby compass needle. Electricity, it turned out, could influence magnetism. Ørsted's discovery, electric currents create magnetic effects, was quickly taken up by André-Marie Ampère in Paris. Within months, Ampère began formulating the laws of electrodynamics, describing how currents attract or repel and how magnetism and electricity were intertwined. A decade later, in 1831, Michael Faraday in London discovered electromagnetic induction. Moving a magnet near a coil of wire or changing the magnetic field through the coil could induce a current in the wire. This principle is the foundation of generators and transformers, the devices that, by the late 19th century, would feed electricity into grids and light entire cities. In the 1860s, James Clerk Maxwell expressed electricity and magnetism in a unified set of equations, showing that light itself is an electromagnetic wave. These 19th century breakthroughs transformed electricity from a laboratory phenomenon into an industrial and everyday one. But the hinge, the turning point that made such progress plausible, lay in the late 18th century, when experimenters like Franklin, Coulomb, Galvani, and Volta turned scattered observations into a common language and toolkit. The kite and key were not a daredevil stunt. They were a conceptual bridge. The Leyden jar, torsion balance, frog leg, and Voltaic pile were stepping stones from spectacle to understanding. By 1800, a curious investigator could not only shock themselves for amusement, but measure, store, and generate electricity in a controlled way, and imagine using it beyond the lab. From that vantage, the telegraph, the motor, the light bulb, and the modern battery were not wild fantasies. They were engineering challenges waiting to be solved. A century that began with sparks from rubbed glass ended with machines turning in factories and lamps glowing in city streets. The lightning of the sky had become, by careful hands and clever minds, a light on a desk.